Dear students, we last day we discussed the properties of relations such as reflexive, irreflexive, symmetric. Now we are going to see the remaining definitions. First of all, we have antisymmetric relation. A relation on a set A is said to be antisymmetric if AB belongs to R and BA belongs to R, then A equal to B for all AB belongs to A. That means, suppose if I have 1, 2 and 2, 1 in a relation, then 1 equal to 2. That is the idea. A relation is antisymmetric if and only if there are no pairs of distinct elements A and B with A related to B and B related to A. That is, the only way to have A related to B and B related to A is A and B the same element. For example, consider the set of all integers with our relation usual less than or equal to. We know that if m less than or equal to n and n less than or equal to m, then we have n equal to m. Now we have the antisymmetric from its metrics and digraphs. A digraph representing an antisymmetric relation if and only if there are never two edges in opposite direction between distinct vertices. That means, suppose I have two two vertices, 1, 2, here it is 3. There are never two edges in opposite direction. That is, suppose I have an edge from 1 to 3, then there is no, we cannot have an edge from 3 to 1. From 3 to 2, I have an edge from 3 to 2, then we may not have an edge from 2 to 3. Okay. The matrix of an antisymmetric relation has the property that if mij equal to 1 with I not equal to j, then mj must be 0. Okay, that means suppose I have a matrix with this is my uh, this is 1, 2, here it is 1, 2, that is in 1, 2, that is I have a relation, I have the ordered pair 1, 2 here, therefore the position corresponding to 2, 1, we have 0, that means I cannot have a ordered pair 2, 1. Okay, or in other words, if either mij equal to 0 or mja equal to 0. Okay, that is, if m12, if m23 is 1, then m32 must be 0, or if either m23 equal to 0 or m32 equal to 0. Okay, that means if m23 equal to 0, then m32 can have either 0 or 1. Okay, if it is 0, m23 cannot take the value 1. Okay, now note that not symmetric is different from anti-symmetric. Okay, now we are checking the idea of symmetric and anti-symmetric relations. The term symmetric and anti-symmetric relations are not opposite. The term symmetric and anti-symmetric are not opposites because a relation can have both these properties or may lack both of them. A relation cannot be symmetric and antisymmetric if it contains some pair of the form AB where A not equal to B. Okay, let us have an example. Let A equal to 1, 2, 3. R and R1 be two relations on A. And R is defined as like this. R equal to 1, 2, 2, 1, 2, 3. Then R is not symmetric. Why R is not symmetric? Because I have 1 2 is here, then 2 1 is here, okay. But 2 3 is here, but 3 2 is not present in R. Therefore, R is not symmetric, which is also not anti-symmetric. Why? 1 2 is here and 2 1 is here, but 1 not equal to 0. Okay, therefore it is not anti-symmetric also. That is, R is a neither symmetric nor anti-symmetric. Okay, now let us have the next example. R1. R1 is defined as 1 1 2 2, which is both symmetric and anti-symmetric. By it is clear because here we cannot have an AB. If AB is present, then BA is also present. Okay, here both elements are equal. Okay, and similarly for antisymmetric. If AB and BA, then A equal to B. Okay. Now these are some examples. Consider the following relations on 1, 2, 3, 4. Which of the relations are antisymmetric? First of all, look, R1 is 1 1 1 2 2 1 2 2 3 4 4 1 4 4. Is it an antisymmetric relation? No, because here I have 1 2 and 2 1 are in R1. AB, BA, but 1 not equal to 2. Clear? What about R2? In R2 also we have the same problem. 1 2 and 2 1 are present, but they are not equal. We cannot say 1 equal to 2. Therefore, both R1 and R2 are not antisymmetric. Then, what about R3? Here also the same problem. Here 1 2 and 2 1 are present, but they are not equal. Therefore, R3 is also not an antisymmetric relation. Then what about R4? We have 2 1, 3 1, 3 2, 4 1, 4 2, 4 3. Look at this relation. Here I have only pairs of the form AB. We cannot have a pair of the form BA. Okay. Therefore, R4 is symmetric, anti-symmetric because 2 1 is present but 1 2 is not present. 3 1 is present but 1 3 is not present in R4. What is the condition for anti-symmetric? If both AB and BA are present, then only we need A equal to B. Okay. Then what about R5? R5 also we have the same thing. 1 2, but 2 1 is not there. 1 3, 3 1 is not there. 1 4 is present, but 4 1 is not there. 3 4 is present, 4 3 is not there. Therefore, we don't need to have 1 equal to 3, 1 equal to 4, 3 equal to 4. Therefore, R5 is also antisymmetric. R6 also symmetric because there is only one element 3 4. Okay. The relations R4, R5 and R6 are all antisymmetric because there is no pair of elements A and B with A not equal to B such that both AB and BA belongs to the relation. Okay, for antisymmetric relations, if AB belongs to R and BA belongs to R, then only A equal to B. Okay, here either AB is present or BA is present. Okay, both of them are not simultaneously present here. And we already seen that R1, R2, R3 are not antisymmetric because 1, 2 and 2, 1 are present but 1 not equal to 2. Now we move on the next examples. Uh, the relations are defined on set of all integers. R1 is set of all AB such that A less than or equal to B. R1 is antisymmetric because A less than or equal to B and B less than or equal to A implies A equal to B. Therefore, R1 is antisymmetric. What about R2? R2 is also antisymmetric because it is impossible that A greater than or equal to B and B greater than or equal to A. Is it clear? If I have 2 1 here in R2, then 1 naught is not present in R2 because the condition is that A greater than B. If 2 1 is there, then 1 2 is not there. Therefore, there is no need of considering 1 equal to 2. If AB is present and BA is present, then only A equal to B. Okay, here only we have A greater than B. That is, here I have only elements of the form 2 1. Okay, we cannot have 1 2 in R2. Therefore, 1 not equal to 2 is not a problem for us. Comparing, considering 1 equal to 2. Now, R3, what about R3? R3 is A equal to B or A equal to minus B. That is, R3 is not a antisymmetric. It's a mistake. I written it is symmetric. It is antisymmetric. R3 is not antisymmetric because 1 minus 1 and minus 1 are belongs to R3, but 1 not equal to minus 1. Therefore, R3 is not antisymmetric. Okay. What about R4? A equal to B. It's clearly antisymmetric because two elements are related with respect to R4 if and only if they are equal. What about R5? R5 is also antisymmetric because it is impossible that A equal to B plus 1 and B equal to A plus 1. R6 is not antisymmetric because 1 2 and 2 1 belongs to R6 but 1 not equal to 2. Therefore, here R3 and R6 are not antisymmetric. Okay. You Now, next we move on the next relation, transitive relation. A relation on a set A is said to be transitive if AB and BC belongs to R, then AC also belongs to R for all ABC belongs to A. Transitive relation from its matrix. A relation is transitive if and only if whenever there is an edge from a vertex x to a vertex y and an edge from a vertex y to a vertex z, there is an edge from x to z. Okay, there is an edge from x to z. Suppose these are my three vertices. This is my xy. Okay, I have an edge. Xy is present means I have an edge from x to y, an arc from. This is my z. Then from y to z also I have an edge. I have an arc. That is I. Then xz is also must be there. That is here I have an edge from x to z. Okay, xy is that is of this form. Not in this way. This one. Like xy, yz, then x is in this direction. Okay. Okay. Completing a triangle where each side is directed edge with the correct direction. Okay. We know that when we are drawing triangle in vector, we draw like that. This means that any diagram of a transitive relation has a lots of triangles. Here we have to define a two new types of matrix. Okay, let E is an m by n matrix with the entries Eij and F is an m by n matrix with the entries Fij with two m by n 0 1 matrices. We say that E precedes or is less than F and we written as E less than or equal to F if Eij less than or equal to Fij for all I and j. For all elements in the matrices, we can compare that elements. Okay. Consider this example. E equal to 1, 0, 1, 0, 1, 0, 0, 1. F is 1, 0, 1, 0, 1, 1. Here 1. 1 less than or equal to 1. Okay. No problem. 0 less than or equal to 0. So okay. 1 less than or equal to 1. Okay. The first two rows are equal. Therefore no problem. Then think of second one. Here 0. Okay, here is also 0 and the condition 0 less than or equal to 0 here. Here it is 0. Here it is 1. We know that 0 less than or equal to 1. 1, 1, 1 less than or equal to 1. That is, all the entries satisfies this condition. Eij less than or equal to Fij. Then we say that these two matrices E precedes F or E is less than or E less than F. Okay. Now, a relation is transitive if and only if mr square is less than mr. Okay, mr square means the matrix corresponding to R composition R. Okay, if a relation is transitive if and only if mr square precedes mr. Okay, now we move on to the next slide. Consider the following relations on 1, 2, 3, 4. Which of these relations are transitive? 1, 1, 1, 2, 2, 1, 2, 2, 3, 4, 4, 1, 4, 4. Okay, here 1, 2 is there, 2, 1 is there, therefore we have 1, 1. A, B, B, C, then A, C. Then 1, 2, 2, 2, 1, 2 is there. Okay, now consider 2, 1, 1, 2, we have 2, 2. Okay, here we have a problem. 3, 4, 4, 1, but 3, 1 is not present. 3, 4, 4, 1, but 3, 1 is not present. Therefore, R1 is not transitive. What about R2? 1, 2 is there, 2, 1 is there, but okay, it's okay. 1, 1 is here. 2, 1 is here, 1, 2 is here, but 2, 2 is not there. A, B, B, C, then AC 2, 1, 1, 2, but not 2, 2. Okay, therefore R2 is not transitive. What about R3? 1, 2, 2, 1 we have 1, 1, 1, 4, 4, 1 we have 4, 1. Then this is the problem. 4, 1, 1, 2. 4, 1 is present, 1, 2 is present, but we have no 4, 2. Therefore, R3 is not transitive. We have explained here. 3, 1, 4, 1 in R1, but 3, 1 is not R1. The 2, 1, 1, 2 is R2, belongs to R2, but 2, 2 is not in R2. 4, 1, 1, 2 in R3, but 4, 2 is not in R3. Therefore, R1, R2, R3 are not transitive. The remaining R4, R5, R6 are transitive. Read this one. R4 is transitive because 3, 2 and 2, 1, 4, 2 and 2, 1, 4, 3 and 3, 1, and 4, 3 and 3, 2 are the only such sets of pairs. And 3, 1, that is 3, 2, 2, 1, 3, 1, 4, 1, 4, 2, 2, 1, 4, 1, 4, 3, 3, 1, 4, 1, 3, 1, okay, 4, 3, 3, 2, 4, 2. And this 3, 1, 4, 1, and 4, 2 belongs to R4. Therefore, R4 is transitive. Similar argument is valid for R5 also. 1, 2, 2, 2. We have 1, 2. Then 1, 3, 3, 3. We have 1, 3. 1, 4, 4, 4. We have 4, 4. 3, 4, 4, 4. We have 3, 4. Okay, therefore R5 is also transitive. R6 is transitive because there is only one element. Therefore, no need of considering AB, BC. There is no. If AB and BC belongs to R, then only A equal to A related to C. Okay, here we have only one element, therefore it's also transitive. Now consider the relations on Z. AB such that A less than or equal to B, which is transitive because A less than or equal to B and B less than or equal to C implies A equal to C. Therefore, R1 is transitive. What about R2? R2 is set of all AB such that A greater than B, which is also transitive because we know that A greater than or equal to B and B greater than or equal to C implies A greater than or equal to C. Okay, R3, A equal to B or A equal to minus B. That is A equal to plus or minus B. Okay, therefore, if A equal to plus or minus B and B equal to plus or minus C, we have A equal to plus or minus C. Therefore, R3 is also transitive. R4, A equal to B. Clearly, it is transitive since A equal to B and B equal to C implies A equal to C. Then R5 and R6 are not transitive because 21 is 21 and 10 are present in R5, but 20 is not in R5. Similarly, 21 and 12 are in R6, but 22 is not in R6. Therefore, R5 and R6 are not transitive. Okay, now we studied all the properties of relations, all classification of relations. What are they? Reflexive, irreflexive, symmetric, antisymmetric, and transitive. Okay. Now we can have questions like is the like this is the divides relation on set of positive integers is reflexive, reflexive, symmetric, antisymmetric, and transitive. Okay, we have already discussed that reflexive because A divides A whenever A is positive integer. We consider here it is as positive integers. Therefore, we know that 2 divides 2, 3 divides 3, and so that is A divides A. Therefore, this relation is divides relation is a reflexive relation on set of all positive integers. What about irreflexive? It is not irreflexive because A divides A whenever A is a positive integer. Therefore, the divides relation is not an irreflexive relation. The reflexive relation means we cannot have the pair AA belongs to R for every A belongs to the set. Okay, here it is true. Therefore, this relation is not an irreflexive relation. What about symmetric? We know that 1 divides 2. Okay, that is 2 is a multiple of 1. But 2 does not divides 1. Okay, otherwise think of 3 divides 6, but 6 does not divides 3. Therefore, it is not a symmetric relation. Symmetric means if A related to B, then B related to A. Okay. What about antisymmetric? If A and B are positive integers with A divides B and B divides A, then A equal to B. Okay, this is true. If A divides B and B divides A, then it must be equal. Therefore, this divides relation is anti-symmetric. Transitive, suppose A divides B and B divides C. Okay, when A divides B, we can say that there exist and positive integers k and l such that B equal to AK. Okay, that is A is a multiple of A divides B, therefore B is a multiple of A. And similarly, B divides C. C is a multiple of B. C equal to B. Hence, C can be written as what is C? We take B equal to AK and C equal to B. Therefore, C equal to we have to replace B by AK. AKL. That is C is a multiple of A. Therefore, A divides C. Hence, the relation is transitive. Okay. A divides B means B is a multiple of A. Therefore, we can write B equal to AK. B divides C means C is a multiple of B. Therefore, we can write C equal to BL. And here we can replace C equal. We can replace B by AK. Therefore, C equal to AKL, which is a multiple of A. Sorry, which is a multiple of A. Yeah. Therefore, A divides C. Hence, this relation is transitive. Now, consider the relation R on the set of integers defined by A related to B when AB greater than 0. Okay, we have to check the relation is reflexive, symmetric, antisymmetric, or transitive. Because the relation is reflexive, because for all integers we have xx, that is x square greater than or equal to 0. Therefore, x related to x. Hence, this relation is reflexive. If it is reflexive, cannot be reflexive. Okay. Therefore, this relation is not reflexive. What about symmetry? If xy belongs to z and x related to y, we assume that xy belongs to z and x related to y. X related to y implies xy greater than or equal to 0, which implies yx greater than or equal to 0, which implies y related to x. So the relation R is symmetric. Right? So here we suppose that xy belongs to R. What is the condition for xy belongs to R? This product xy greater than or equal to 0. We know that xy greater than or equal to 0 implies yx greater than or equal to 0, which implies yx belongs to R. Therefore, xy belongs to R implies yx belongs to R. Is it anti-symmetric? No, because 2 into 4, 8 greater than or equal to 0, and 4 into 2, which is also 8 greater than or equal to 0, but 2 not equal to 4. Therefore, it is not anti-symmetric. If AB belongs to R and BA belongs to R, then A must A equal to B, which is not found here. What about transitive? 3 into 0 greater than or equal to 0, into 0 into minus 7, which is 0, which is greater than or equal to 0. 3 into 0 is 0, which I can say greater than or equal to 0. 0 into minus 7, which is 0, greater than or equal to 0. But AB belongs to R and BC belongs to R, then AC. What about AC? 3 into minus 7, which is minus 21, less than 0. Therefore, this relation is not transitive. Okay. Now, we have another problem. A equal to 1, 2, 3, 4, 5. Give an example of a relation R on A that is reflexive and symmetric but not transitive. Next one, reflexive and transitive but not symmetric. Symmetric and transitive but not reflexive. Okay. Here we define like this. Reflexive means we have the relation must contain 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Therefore, first of all, we write 1, 1, 2, 2, 3, 3, 4, 4, 5. Reflexive and symmetric. Symmetric means if I write 1, 5, we have to add 5, 1 also. Okay, 1, 5, 5, 1, 5, 3, 3, 5. Okay, if I write 5, 3, then I have to include 3, 5 also, which is not transitive because what is the reason? 1, 5 is there, 5, 3 is there, but 1, 3 is not in R1. Therefore, this relation is not transitive. Okay, if you supposed to write a relation which is reflexive, you have to include all the pairs of the form AA. Okay, that must therefore the relation must contain 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Okay, then you have to add, then it is reflexive, symmetric, and transitive. Okay, if you have only 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, that relation is both symmetric, reflexive, and transitive. Okay, um, it is transitive because there is no pair of the form AB, BC. Okay, therefore, you have to make it is not transitive. You just add one more element here. Okay, 5, 3 and 5, 1. Therefore, you cannot have 1 in the 1, 5, 5, 3. Okay, then only this relation becomes not transitive. Is it clear? 1, 5, 5. If you add an element here, for being symmetric, you have to add its opposite way. 1, 5, AB, then you have to add BA also. 5, 3, 3, 5. Then reflexive and transitive. reflexive and transitive, but not symmetric. Reflexive means you have to add all the pairs of the form 1 1 2 2 3 3 4 4 5 and transitive. Okay, I add 1 5 here, therefore 1 1 1 5 1 5 is there. Okay, which is not symmetric because I included an element 1 5 here, but I did not add its opposite a b a 1 5 here, but 5 1 is not there, therefore it is not mm, symmetric. Okay, ഞാൻ സിമെട്രിക് ആകാതിരിക്കാൻ വേണ്ടി എന്ത് ചെയ്തു 1 5 ആഡ് ചെയ്തിട്ട് ആരെ ആഡ് ചെയ്യാതിരുന്നു 5 1 ആഡ് ചെയ്യാതിരുന്നു. ക്ലിയർ ആയോ? അപ്പൊ അയാൾ ആരാകാതിരുന്നോളും? സിമെട്രിക് ആകാതിരുന്നോളും. Now symmetric and transitive but not reflexive. Not reflexive means in the set we cannot have 1 1 2 2 3 3. ആരെങ്കിലും ഒരാൾ ഇല്ലാതിരുന്നാൽ മതി. Here we cannot have 2 2 ഇല്ല, 3 3 4 4 5 5 1 5 5 1 1 1. Okay, symmetric ആയിരിക്കണം. Therefore I add 1 5. If 1 5 is there, 5 1 is also there. Okay, it is symmetric because 1 5 belongs to R3, 5 1 also belongs to R3. Transitive 1 5 5 1 1 1 5 1 1 5 5 5. Not reflexive because 2 2 is not present there. Okay, now we have to remember these relations. We have to find the number of relations on a set having these properties. Let A be a set having n elements. Then number of relations on A is, we know that 2 raised to n into a, that is 2 raised to n square. If suppose A is a relation, R is a relation from A to B and A having m elements and B having n elements, the number of relations is 2 raised to ma. Here m and n are equal, therefore 2 raised to n square. Then in which the reflexive relations on A is 2 raised to n square minus n. Number of reflexive relations on A is 2 raised to n square minus n. Irreflexive relations on A is the same, 2 raised to n square minus n. Symmetric relations on A is 2 raised to n square plus n by 2. N square plus n by 2. Reflexive and symmetric relations on A is 2 raised to n square minus n by 2. Antisymmetric relations on A is 2 raised to n into 3 raised to n square minus n by 2. Asymmetric relation, that is asymmetric means not symmetric, opposite of symmetric. Asymmetric relations on A is 3 raised to n square minus n by 2. Relations which are neither reflexive nor irreflexive on A is 2 raised to n square minus 2 times 2 raised to n square minus n. Total we have 2 raised to n square elements. Then neither reflexive nor reflexive. That means I subtracted both reflexive and irreflexive. We have reflexive, we have 2 raised to n square minus n, and reflexive we have 2 raised to n square minus 1. Therefore 2 raised to n square minus 2 times 2 raised to n square minus n. You have to by heart this result. Okay.